In nonlinear optical microscopy, we're usually focusing down a beam to a diffraction limited or close to a diffraction limited spot. In microscopy, we're usually focusing light down and scanning it, and as a result, the optics in the focal volume are not typically identical to those used in the far field. And we're going to consider a common case of a Gaussian beam profile that then gets focused down to a spot through a low NA objective. And we're going to do the low numerical aperture objective first. That's consistent with what's called the paraxial approximation. And in the paraxial approximation, all that is really saying is that sine theta is roughly equal to theta, where this is theta. And the math becomes a lot easier in that approximation. In brief, what we'll find is that the polarization state, if I have a polarized source out here, that polarization is retained within the paraxial approximation within the focal volume of this Gaussian beam. And when we want to just sort of see what happens, I'll tell you the net result is that we can, in this limit, neglect the fact that we're focusing down with a Gaussian beam when describing the relative polarization dependence. But we want to convince ourselves of that and lay a foundation for the use of Gaussian optics when it comes to describing phase shifts. Okay, I mentioned the paraxial approximation. And how does that manifest? I'm not going to go through the derivation. I'll just give you the end result here. And the short answer is that the electric field, as a function of, let's see, this would be rho, distance away from the center. This is with assuming cylindrical symmetry, and z, if the beam is propagating in this direction. The electric field at any position as a function of those two coordinates is given by the incident polarization state and this factor c, which depends on those two coordinates. And the expression is kind of lengthy, but there's a couple of key parameters that really dictate the overall characteristics. The first is the Rayleigh range, which is z0, and that's essentially 2 times z0 is essentially the depth of field. So z0 represents the width of this beam along the axis of propagation, and w0 represents the beam width. 2w0 is the beam waist in the focal plane. And those two parameters, with those two parameters in hand, and those are actually determined by the cone angle of the incident light, which is also dictated by the numerical aperture of the objective. So everything sort of ties into that one parameter, the numerical aperture of the objective, and that dictates both z0 and w0. So if you know theta 0, you can generate all the rest of these and therefore describe the electric field as a function of position within the focal plane. Now we're just going to consider what happens if I have an object positioned right here in the center of the focal point. And I'm also going to assume that it's thin, so it's simply a polarization sheet that we illuminate and generates SHG or some frequency in the direction in which we're detecting. And we want to describe how to relate the corrections, if any, with respect to the polarization state coming off of here and what we measure after we collect through the objective in the far field. So based on these equations, the local electric field in this as a function of position and in cylindrical coordinates in the focal region is dictated by the incident polarization state, and then that's just projected with this one-to-one correspondence and then rescaled by this factor describing the change in position. But the polarization state itself is actually unaffected because of this 1, 0, 0, 1, 0, 0 component. There is no z component of the field because that's the component along the direction of propagation. We can invert this and think of it the other way around as well. If we wanted to ask what correction we would have to apply in order to account for the deviation between the far field and the local electric field, it would just be the inverse of that. Well, not really exactly the inverse because it's not an invertible matrix, but it'd be an equivalent invertible matrix 1, 0, 0, 0, 1, 0 to convert from the local frame back to the Jones frame and then multiply by 1 over that same scaling factor. And we can do that for both the fundamental and the second harmonic. We're generating a local electric field in the focal volume, and then we want to relate that back to what we detect in the laboratory frame. This is the way you do it. Now, in nonlinear optics, it's all about projection. So how do we relate this framework into this architecture that we already have built up? where we have a Jones vector, and that's related to the local frame tensor, and this is the prime one with all 27 elements, through a Fresnel-Factrix matrix that we just talked about in the preceding lecture, 1 or 2 lectures ago, and J. And what is J? J contains 2 terms. The first is the rotation from the local frame to the laboratory frame. So for example, if this is vertical and horizontal, and I have some Z local frame tensor, then this rotation matrix describes, for example, rotation about phi to convert from the local frame to the laboratory frame. And then we kill everything that has a Z component in it. And that's basically what this truncated identity matrix has done when it was first introduced. But now we can take that same idea and just generalize it to include these corrections within the paraxial approximation. So instead of it being just this part, we're going to also include the scaling. And this also helps illustrate, hopefully, where this 1, 0, 0, 0, 1, 0 matrix came from in the first place to connect the Jones frame to the Cartesian frame. But now we're actually explicitly including the scalar component. So the good news is that as long as we're talking about ratios of tensor elements, then the fact that everything is simply given by a simple scalar, as long as all of our sources is in one place in the field of view for all our observables, all of our different polarization-dependent observables, and we only really care about ratios of tensor elements, and the absolute magnitude of this K doesn't really matter all that much, especially since we're using normalized vectors for the incident Jones vectors in the first place, and hopefully we'll recover normalized Jones tensor elements. So this K, in some cases it does matter if you're actually looking at quantitative differences in the intensity. But for polarization-dependent phenomena, because the polarization within the focal region is identical as the far-field polarization, it's simply a scaling factor that we can largely ignore. Gaussian optics and the paraxial approximation, they are worth their weight in gold.